Please welcome Lisa Stright.
All right. Well, thank you, Maury, for the introduction. It's my pleasure to be here today to talk to you about the science of oil and gas, or otherwise known as Petroleum Geology 101. And it's my hope by the end of this talk that you'll come away with three things: a feeling for some of the resources of oil and gas that we have here in Colorado, and an understanding of the science of oil generation, migration, and storage in the subsurface, and some of the challenges that we face in bringing it to the surface and to market. And then finally, I want to end on some discussion of the balance of production and consumption, both global and in the US. So with that, let's step into the resources that we have here in Colorado. And what you see here is a map of oil and gas fields within Colorado. The yellow blobs are what we call sedimentary basins that contain these oil and gas resources. The red and the green are the oil and gas fields. Just to orient you, in case you're unfamiliar with the area, the yellow star is approximately where we are today. And so in our backyard here along the Front Range, we have a basin called the Denver Basin. And we have some prolific oil and gas reservoirs within the Denver Basin. So just to give you a feel for some of these resources in Colorado, Colorado has 10 of the largest 100 gas fields in the United States. So we have quite a few large gas fields, and 3 of the 100 largest oil fields. We produce a tremendous amount of gas from coal bed methane as well. So this is gas that comes out of coal. And so that points to the fact that we also have a significant coal resource in the state as well. We are 3rd and 9th, respectively, in gas reserves and oil reserves. Now, these are 2008 numbers from the Colorado Geologic Survey, so they might have changed in the last couple of years. Now, I want to kind of bring to your attention this idea of a sedimentary basin and what a sedimentary basin is, because this is critical to understanding oil and gas reserves. And so what we're going to do is we're going to step into looking at the upper northeast corner of Colorado in the Denver Basin. And I want you to look at the cross-section A to A prime that goes between Greeley and Denver. And we're looking at a cross-section in the lower left image where you see we're going from the mountains in the west out to the plains in the east. And what we see in there in this yellow layering in the center is the deposits of a sedimentary basin. Whoops. And on the right, what you can see is the column of named horizons of those deposits. And you're not going to be able to read this in detail or understand it yet, but what I want to draw your eye to are the yellow sections are zones of where in depth we're generating oil and gas, or have generated oil and gas historically in geologic time. And in green and red and blue are reservoirs of where oil and gas exist. Okay. Now, if we look at some of the geology that actually outcrops in Colorado, we have this fantastic opportunity to see some of these rocks that are in the subsurface actually brought up to the surface. And you can see in the image on the bottom left where the yellow layers start to curve up to the surface. That's how we're getting to see these rocks that are actually reservoir rocks down in the subsurface. So, for example, this image is at 285 and C470, and you can see that we're looking at the upper layers of the Muddy J Sandstone and the lower layers of the Skull Creek Shale. Okay, and so you can go walk up and look at reservoir rock and source rock yourself if you're interested. But the other part that's really interesting about this is if you go up to these rocks, you can actually see oil seeping out of them. And I'm a native of Colorado, almost, close to it, but I never knew at this location there was oil seeping out of these rocks until I started doing this research. At the end of this talk, I hope you have enough information to go to your neighbor and explain geologically why and how this could happen, okay? So in order to explain this, we need to start thinking about the birth of the organic material that makes oil and gas. And so I have to go back millions of years in time. And first, I have to address the fact that no, this organic material does not come from a mass extinction of dinosaurs. While a mass extinction of dinosaurs did occur, the majority of the organic material came from vibrant sea life. That was microorganisms in the ocean column that died and fell and accumulated on the base of the ocean floor into an organic, rich, muddy layer. Furthermore, plants on the surface could also contribute to that organic material, either in the ocean basins or on land, and be converted to coal resources down the road. Now, this organic material is preserved through oxygen-poor water, but then it's also preserved because then it's further buried by sediment. Now, what is sediment? Now, you can imagine a case where, and this is similar to the geology of Colorado, through time we've had processes of mountain building, where we create potential energy for wind and rain and freeze-thaw cycles to break down the rock into smaller particles or sand grains and carry them along rivers into these sedimentary basins. And so what I show here is a thick sand layer that's accumulated by these processes on top of this organic-rich mud layer. And by that pressure of the sand column on top of that organic mud-rich layer, we're compressing that organic-rich layer, but then we're also burying it a little further and increasing the temperature. So this continues to happen through multiple cycles of uplift and climate changes where we fill the basin with alternating layers of sand and shale. And we're increasing the pressure and temperature with depth each time we do this on the organic rich layer, but then also on these sandy layers. Now, what happens with the sandy layers is that as we increase the pressure and temperature, we're compacting the grains together and also cementing them. So they go from a loose sand, again, that you might find on a beach, to now a sandstone rock. And what you see in the lower left is an image of what a sandstone rock would look like. And something called a thin section, which is a view of the individual grains in this sandstone rock, which are white, and the pore space between those grains, which is blue. So originally, this pore space is filled with salty water because these grains were deposited in an ocean basin. Okay? And so we refer to this as porosity. And this will be the future storage location for oil and gas. Now, the other property that these sandstone layers have is that they are also very permeable. What that means is that the fluids can actually flow through these grains. And it's hard to believe when you look at an image like that on the lower left that you can actually not only contain oil and gas in those pores, but you can actually move those fluids through there. Now, conversely, when we look at the fine-grained shale layers, we have very limited permeability. One of the reasons is that shale layers are shale particles are more platelet in nature. And so then when you compact them, it's almost like stacking multiple sheets of paper on top of one another. And they're also much, much smaller than sand grains. So what that means is when we start to compact the shale layers, we create something that's called an impermeable layer, okay, whether it's organic rich or not. And it essentially means that we cannot very easily flow fluids through it. This actually works in our favor in the subsurface for oil and gas accumulations. Okay, so we're going to continue now to bury this organic rich source rock further and further into the basin. And maybe we also have, instead of just mountain uplift, we have some basin compression that starts to bend and contort the layers. And this will be important, and you'll see why in the future. And as we bury this organic-rich layer, the carbohydrates and proteins of the organic material starts to break down. And we end up with two main constituents. Kerogen, which is an insoluble organic material that's very waxy in nature, and bitumen, or black tar. Bitumen is what's produced in the Athabasca tar sands in Canada. So it's just a very immature oil. So we'll continue to bury that source rock further down until we hit something called the oil window. And so with increased temperature and pressure with depth, we start to convert that kerogen, that organic material, into the constituents of oil and gas. And what you see here is that we've got paraffins, cycloparaffins, and aromatics that make up some of the main components of oil and gas. The main reason I want to point this out is to point out that something like benzene is actually a naturally occurring component of oil and gas. And so when you're at the gas tank and you're breathing the fumes, you're actually breathing benzene, which is a known carcinogenic. Okay. And so then as we generate more and more oil, there's a very small animation there where you see oil droplets start to migrate out of that source rock. And what they do is, because they're migrating into a sandstone with water in the pores, they migrate up to because they're less dense than water, up to a point where they can't move anymore when they hit that impermeable shale layer. Okay, it's not unlike putting a drop of oil in the bottom of that glass. You would expect for that drop of oil to float to the top. And this is where the impermeable layer works in our favor, because it traps the oil and gas. And this is our first sign of an oil reservoir. But we can continue to bury this basin even further, just with increasing subsidence, for example. And you see the two blue stars, keep your eye on those as we move to the next slide. And the source rock on the left has been buried even deeper, and the reservoir on the right has been buried deeper as well. So similar to having an oil window, with increased pressure and temperature, we also start to break down the components of oil into gas. And so this is what we would call a natural cracking process. And to illustrate, what I've shown is just a long chain hydrocarbon, and the increased pressure and temperature is going to start breaking that down into its more basal constituents: methane, ethane, propane, and butane. So getting into the gas window. If we bury it too far, where the blue star on the left shows you, we've actually overcooked the hydrocarbon. So it's akin to burning the toast. Okay? And so that rock is no longer going to be generating any hydrocarbons. But as we move to the right, you can see a very nice part of that organic rich layer that's now in the gas window. And moving even further to the right, you see the layer is in the oil window. And gas and oil begin to migrate out of those source rocks and into the reservoirs. Okay? And so now we have reservoirs that have both oil and gas. What I've also shown is the possibility of secondary migration through something like faults. So a fault could be a conduit whereby gas or oil could transfer up to that next layer. So another possibility. And so then this takes me back to the example by C470 and 285, where we saw oil coming out of the rocks. There's also the possibility that we may not trap the oil and gas, and that it could escape either through the faults or through where the geology outcrops to the surface. And so this is one plausible explanation for what's happening in that location at 285 and C470. Okay. So one point that I want to make is that this process that I've showed you is not an overnight process. This is a process that occurs over geologic timescales of hundreds of thousands to millions of years. So in a sense, this is not a renewable energy source. Okay. Further complicating this as a resource is that what I've shown you is actually very oversimplified for these yellow layers. What I've kind of presented makes you think that all of what's in the yellow is actually really nice, homogeneous sandstone. But in reality, what we have is in the lower left image, there's different processes, rivers and deltas, for example, that will carry these sand grains into the basin and distribute them unevenly as the basin fills through time. So you might have the nice yellow areas in the lower left image are sandstone bodies separated by shaly zones. And so you can imagine if you wanted to drill a well through that and take all of the oil out that is in each of those yellow bodies, it's going to be very difficult to do it with a single well. Okay? So what that leads me to is that out of the 100 barrels of oil, for example, that we have in the subsurface, in these different depositional environments, geologic settings, we're leaving a significant amount of oil in the ground just due to the geologic heterogeneity and complexity of these reservoirs. And this is an exciting area of research where we can really spend a lot of time trying to understand the geologic processes better to do better predictions of where these sand bodies are so that we can optimize the number of wells, minimize the number of wells that we drill, and optimize production to minimize our footprint. Okay, so let's take a step back and now start to look at the global view of petroleum geology and world reserves. So I want to point out two different terms. One is the term reserves and one is the term resources. Okay, so first, let's talk about resources. Global resources are all of the hydrocarbons and all of the sedimentary basins in the world, whether we know about them or not. So it's everything that exists. We can't actually call them reserves until we can economically, politically, environmentally, and technologically pull them out of the ground. And at that point, we can actually call them reserves. So reserves numbers change. And they change quite frequently. Because if, for example, the oil price changes, the reserves for a country might change, for example. Okay, so you'll see in this list, a list of the world oil reserves. And the US, we're number 11. Okay. And now if we move to thinking more about production, we've got world oil production on the left and world oil consumption on the right. Although the United States is 11th in reserves, we're actually really efficient about producing our reserves, and we're pulling a lot out of the ground. So we're number 2 in production with about, I'm having a hard time reading my numbers, but it's about 11 million barrels. But we're the number 1 consumer at about 18 million barrels. So the thing that's interesting is this gap has actually been closing over the last couple of years. And this is why. So this is a graph from the EIA. On the left are crude oil production, imports, and reserves in the US, going from orange, blue to green. And on the right is natural gas. The vertical axis is in billion barrels of oil on the left and trillions of cubic feet on the right. And so what you can see is in the crude oil sense that up until about 2007, we were in a place where our imports were increasing significantly and our production was decreasing. Okay, that was because we were producing more and more and more of our available reserves. But then all of a sudden that turned around. And you see that same turnaround on the gas curve with the reserves. And this is a case of new technologies coming to play where we can actually start producing some of the previous resources and turning them into reserves and pulling that oil and gas out of the ground. And so this is where we introduce the term conventional versus unconventional. So in a conventional play, we're going after those sandstones, drilling into those nice pockets and pulling them out of the ground with some of the challenges that I mentioned to you before. And because we have high permeability, those fluids more or less flow directly to the wellbore. But now we're kind of stepping in and saying, hey, we've got some porosity with some oil and gas in those source rocks. How about we go after those? And so we have some new technologies that allow us to enhance the permeability to make it possible to flow those fluids to the surface. And this is something that my co-convener, Rebecca, will speak to more. Okay. So I'd like to finish with this one thought, and this is a slide from Scott Tinker at the BEG. And I love the way it illustrates how much we consume as a society. So this is an image of an oil tanker with 750,000 barrels of oil. It's about 50 Olympic swimming pools. In 2011, this amounted to about 13 minutes of global oil consumption. Okay. I redid this for 2015, and I came up with 5 minutes of global oil consumption for that same volume. So this either illustrates that I used drastically different assumptions for my calculations than Scott Tinker, or that we've got an increase in consumption worldwide. Okay. And if we step to the next slide, I think that my calculations aren't too far off from Scott Tinker's, because you can see that our global energy demand is increasing significant, driven largely by economic growth in Asia. The other thing to point out is that the United States, this tanker would last about an hour. Our consumption is double the rate of the world overall. The world consumption is 31 barrels of oil per person, per 1,000 people per day. And in the United States, it's 61 barrels of oil per 1,000 people per day. Okay. In the Denver Front Range, this amounts to about 3 days, and in Fort Collins, about 3 months. Okay. So the question is, what is our future energy mix? How do we factor in these non-renewable resources and start to look at some of these other renewable resources? And this is an exciting discussion that I know will come up quite a bit within this conference. And so I'd like to end with one point, one take-home point, that it took Mother Nature tens of millions of years to create the efficient fossil fuels that supply over 80% of the global energy demand today. And humans will probably consume it all in less than a few hundreds of years. Thank you.
Good afternoon. I want to thank Mari and CSU, thank all of you for being here. I really appreciate the opportunity. I'm Rebecca Johnson, and I'm going to give you a quick overview of drilling and hydraulic fracturing. I just want to give you a real quick snapshot of who Anadarko is. I'm always so proud to share our mission statement and our values because they really reflect a company that understands it's not always about us. So our mission recognizes that affordable energy is fundamental to physical existence. It's as important in life as food, water, and air, but it's something that we often take for granted. And our values guide us every day as we make decisions, and it's the central reason why our company makes Denver's top workplace for the last 3 years running, and this year it was named to Forbes' list of the world's most innovative companies. So today, this presentation to me, is all about open communication, and it's about the opportunity to share what I do for a living. So again, I'm Rebecca Johnson. I'm a completion engineering advisor, and I've been fracking for 23 years. So I'm not a professional speaker. I'm really a very geeky engineer. But I'm here today to share with you what I do for a living. And it's a pretty simple process. So we mix water and we mix sand, and we put it through pumps and into the casing and into the ground, and we frack the rock. And that is what cracks the rock in order to make the oil and the gas come and produce back up through the casing and into the pipeline. So I'm going to go through that. So before we get into those details, I want to add a little bit more to Lisa's really great presentation. And you probably already know this, but as a nation, oil and gas provides 65% of our energy needs. And if you haven't already done so, I would highly recommend reading The Moral Case for Fossil Fuels. Has anybody read this by Alec Epstein? Yeah, it's a great read. Even as an engineer, I can read it. And the first chapter is free on his website. But it's a great book, and that he's written about the bigger picture on our use of energy, and in particular, fossil fuels. This is a little video. This describes, it's just a quick video of what Lisa described. And so as we turn it on, this is essentially just the deposition of the biomass. And then if you look at the upper right corner, that's really kind of a map of how it's changed our continent. So does everybody know that there was an inland sea and that Colorado was a part of the inland sea? And so this is a description, a quick overview of the reservoirs that were deposited right here in Colorado, right on the eastern slope. And so right there on the right-hand side, those are all the reservoirs from the Fox Hills to the Parkman, Sussex, Niobrara, and J-Sand. So now you can see it heating up, and the mountains, and then the Fox Hills aquifer, and then there's Denver, and the reservoir is 7,000 feet below the surface. So I'm going to go through step by step, just real quickly, the process of drilling and completions, which includes fracking, and then leading to the production. And so first we have a drilling rig, and that's 10 to 20 days per well. And then we have a completion, And that includes the hydraulic fracturing, which takes 1 to 4 days per well. And then we move on to a producing well that's there for 20 plus years. So I want to tell you a little bit more about myself. I grew up in Colorado Springs, born and raised, and I came to CSU, and I got my degree in chemical engineering. And I've been blessed to work my entire career here in Colorado in the oil and gas industry. So I live in Berthoud, Colorado, which is just south of Loveland, and it's really a nice small town. And I've got to tell you that I never really had any intention to work in the oil and the gas industry. I got an internship at Amoco while I was here, and I worked in a plant, and then I got to work on completions in the Denver office, and I was hooked. I loved it. And it's, I've been a completion engineer for the majority of my career. So I have literally been on site supervising probably close to 1,000 fracks during my career. So that's why I'm here to tell you really what I do for a living. And it is such a great job. It is so challenging and therefore so much fun because of the geology, right? And so when I find out, excuse me, what I find out is that when I talk to my family and friends, neighbors and church family, there's a lot of miscommunication about fracking. So most of you probably know what I'm going to talk about today, and a lot about hydraulic fracturing. But hopefully I can give you just a couple more ways to talk to your family, friends, and neighbors. So let's start with some basic facts about Colorado. How many wells are there in Weld County in the DJ Basin that Lisa pointed out? There's over 22,000 wells right there in Weld County. Did anybody know that? I bet a few of you did. Okay, so when was the first well drilled in Weld County? About 1970. So with the multiple formations that I just showed you, from the J Sand all the way up to the Sussex, you can imagine that wells have been fracked multiple times. And so literally, there have been hundreds of thousands, tens of thousands of wells fracked safely from the start right here in Colorado for the last 45 years. So we use this natural gas, of course, right here to heat our homes. And my next door neighbor, I found out he's retired now, but he worked for Xcel Energy for 30 years. And he hooked up natural gas pipelines to our homes. And so he was talking to me about fracking one day as we were out in our yards doing some yard work. And I assumed, of course, that he knew all about this. He's done this for years. But he did not know that the natural gas that we have in our homes comes directly from Weld County. And he did not know that it comes from 7,000 feet deep in the ground. So again, it's just something to pass on and to make sure you share with your friends and neighbors. Okay, so now you know all about the geology, and so that starts the process. And of course, that's extremely important because that is what I depend on, is the geology. So next, we drill a well. We move on a rig, and we use a bit to drill the rock. We start by drilling below the aquifer, about 1,200 foot, and we run steel pipe below the aquifer, and then we pump cement in between the casing and the formation. And these two layers protect the groundwater. Then for a typical Niobrara well, we drill down 7,000 feet, and we run another string of casing, and we pump cement again to surface. Then we drill out horizontally for 1 to 2 miles, and then we run another string of casing and cement around it. So we have 6 barriers between the groundwater and the oil and the gas. And of course, all of this is designed, lots of engineering goes into this for the grade and max pressures for the casing and the cement. So let's go into that in pictures because it's a lot easier. Okay, so here's a vertical well. You move on the drilling rig, and the vertical well starts, and then it drills down, and it drills down through that Nibura. So that Nibura and Codell right there is about 250 foot, and that's the contact that that well has with that reservoir. So the horizontal well is essentially the same thing. The drilling rig moves on, and it drills down to the point that we call a kickoff point. And then we drill through that formation for 5,000 to 10,000 feet. So you can see that in this case, that 5,000 to 10,000 feet is a lot more contact area, right, of that reservoir, which is where we get our oil and gas. So drilling horizontally also reduces our surface disturbance. We can have 4 or more wells on one site, and then therefore it reduces the surface disturbance compared to that vertical well. Okay, so that was drilling. So now as a completion team, we move on location, and what's absolutely critical to us is the integrity of the well. So we test the casing, and we run a cement bond log to ensure the integrity of the cement. And then we design the completion, and then we move a frac crew on and frac the well. And you can see the fracs happen down there. But the majority of the unconventional horizontals are in the Nibura and then the Codell. Has anybody ever seen the Nibura? I bet you have. If not, this is the Nibura. So I'm going to leave it up here so we can talk about it. But this is where we get oil and gas. Did anybody expect it to look like that? These are actually 2 pieces. One's from Wyoming and one is from Aurora. And so this doesn't look like reservoir rock, does it? This is really, really dense rock. It doesn't have a lot of permeability. It doesn't have a lot of porosity, just like Lisa told us. And so that is why we have to hydraulically fracture that, because there's oil and gas in there, and all we have to do is crack it, and then it's able to produce it. So a little bit more about hydraulic fracturing. As I said, you probably already know again, it's water and sand, and it's pumped at a high enough pressure down the casing and into the formation. And that fractures that Nibura. We use sand as a proppant to hold open the cracks in the rock. And then the water is just used to carry the proppant. And it's really that simple. I've also got some samples of the sand that we pump. This is 3050 sand. We also have 4070 I can show you. But I think what you can see pretty quickly if you come up here and look, and I usually pass it around, but I know we have a really big group today, that there's a lot of pore space here. So you can imagine cracking that Nibura, then you put that sand in there, and it holds that crack open, and it creates a pathway for that oil and the gas to produce back to the casing and up the wellbore. So this is a fun equation, and you can see that the pressure needed to break down that rock is relatively simple, but it's really just a function of the properties of the rock. It all goes back to geology. So this is, again, what we do for fun on Saturday nights. It's fun engineers. But here's maybe a different way, a visual, to talk about oil and gas. This is the matrix rock. This would be the Nibura. And this would be the oil and the gas flowing through the tight rock with a well being that's just been drilled in the middle. So it takes a very, very long time to get to that wellbore. If we fracture that rock, of course, we create those pathways so it's able to get to that wellbore a lot quicker. So the way I like to talk about it with my friends and neighbors is it's like our highway system. So remember that sand, when it props open the fracks, it's creating the highways for those molecules to get to the wellbore faster. Does that make sense? I hope that that helps, maybe something, an easy way to pass on about what a fracture system is to your friends and neighbors. So this is a picture of a typical location and the equipment. And so again, we're taking 99.5% water and sand and mixing it with 0.5% of chemicals. We're mixing it in a big blender, and it's a lot like you have, the one you have at home, it's just a lot bigger. And mixing it up, then we put it through hydraulic pumps, and those pumps bring it up to a high enough pressure, and then it pumps down the casing, and then into the formation. It's a high enough pressure to crack that rock. And again, the sand is left in the crack, and the water is just pumping that sand down there. So I'll describe this location a little bit more for you. The red tanks is where we store water, and to the right is the storage for the sand. This is a Halliburton location, and so those are called sand castles. You can see the frac additives at the bottom of the page, and in the middle is the blender. So it's literally water and sand mixed together in the blender, 99.5%, 0.5% of the frac additives, the chemicals. It goes up on your screen into the frac pumps, and then it's going to go in through the wellhead, down the casing, 7,000 feet, out 5,000 to 10,000 foot into the formation, and then it's going to crack that formation. The oil and the gas can then be produced and will come back up the casing, up to the surface, and into the pipeline. The vehicle on the right-hand side is the frac fan, and that's where we monitor everything. So this is where we are monitoring our pumping rates, our pressures, the concentrations of everything. And it's really easy to walk into a frac van and see everything that's going on. So what's in frac fluid? So remember, when we frac, we're mixing 90% water, 9.5% sand, and then 0.5% ingredients. That 1/2 of the 1% ingredients is to reduce the friction on the pipe, so it's called friction reducer, and then to disinfect the water. And sometimes the rock is difficult to crack, as Lisa said. And so if we're not able to pump the water very fast, then we use a gelled fluid to carry that sand. And it's similar to how mandarin oranges float in Jell-O. And basically that's the gelled fluid in the sand, and we're trying to get the sand down into those cracks, right? And so we're just holding that sand and pumping it into the rock. So again, to create the pathways for the oil and the gas to flow up the well. By Colorado law, the industry is required to share all of the ingredients used to hydraulically fracture each well. So FracFocus.org, it's a great site. You can go on there, you can type in any well name, and you can find out exactly what's been pumped, what volume, and find out exactly, look at the CAS number, and then look up at the material safety data sheet. So on a relative basis, oil and gas uses a small amount of water. In Colorado, the majority of the water use is actually 85% is for agriculture, of course, right? About 7.5% of Colorado water is used for municipal. And hydraulic fracturing uses 0.1% in Colorado. So, does fracking cause earthquakes? This is in the news a lot. So, experts agree that fracking is not a source of concern for earthquakes, and here's why. In fracking, only a limited volume of water is pumped into the formation for each stage. Each pumping stage is a one-time event lasting 2 to 4 hours. And of course, the low permeability of a shale reservoir limits the fluid flow to about 300 to 500 foot. There are a number of studies that are evaluating a possible correlation between wastewater disposal and increased seismic activity. And this is still an active area of study, and we're involved in that study. So back to groundwater protection. We've gone through most of this, but I think it's good to just pass on some of the facts. So I know most of you know that fracking first started in 1947 out in Kansas. There have been over 1 million fracks in the US, and it does occur more than a mile below the surface. And again, we have 3 layers of casing and 3 layers of cement that's safeguarding that groundwater. So this slide says it applies to about 95% of all wells in Colorado, but I want to let you know that personally, that during my career, the last 23 years, every well that we've ever drilled, we have fracked. And with the tight rock, that Niobrara that I showed you, that reservoir won't produce without fracking. And so hopefully that makes sense with just seeing the geology. All right. So there are a lot of economic benefits that hit home. Of course, for oil and gas production, there are taxes, of course, that fund public schools, outdoor resources, and roads. And with the oil and gas produced right here, the average Colorado household energy cost is 23% lower than the national average. And so that's about $1,200 on the average of savings. And of course, producing it right here reduces what we import from outside. So I really appreciate the opportunity to share this with you today, and I'd be happy to talk with you afterwards and show you the samples of the Niobrara and the sand samples. But if you have an organization that you would be interested in sharing this with, there's an email address right here at ambassador@anadarko.com, and we'd be happy to meet with your organization and share this, share the facts about fracking. Thank you very much.
Well, thank you. I'm hoping there's some questions out in the audience or perhaps in the live viewing streamers. Remember, the event app is taking your questions. You can type it in under live comments. And I've gotten a few, it looks like. So be thinking about some questions here in the room, if you would, please. But let me ask this question, and I'm not sure who would like to handle this. Maybe you, Rebecca. Could you talk about subsidence? Could extraction lead to subsidence and earthquakes? Lisa?
Am I on? Can you hear me? Okay. So I think, so the question is asking about something called subsidence. And so the idea is that as we pull fluids out of the ground, that the rock can compress further, that what's happening is the fluid pore pressure is actually holding the rock, supporting the rock. And so as we pull the fluids out, then essentially what could happen is the surface could subside. And this has happened in many reservoirs across the world. One of the examples that comes to mind is a diatomaceous reservoir in California. Now, diatoms are these little itty-bitty kind of plant or little marine life that contained oil and gas and highly compressive. And so when that oil and gas was pulled out, the surface subsided. So it subsides. It is possible. The link to earthquakes, I can't think of a direct link in my mind with subsidence and earthquakes, but that is a potential risk depending on the geologic formation.
Is there another question from the audience? I think Jane is walking around with a microphone right here. If you'd raise your hand. And if you have somebody specific you want to ask it, please refer to Lisa or Rebecca.
Hi, my name's Mike Fox, and I was wondering, when you talked about the cementing and the various levels of casing, how do you actually assure that you have cemented it completely so there aren't leaks? Is there a technology to do that, or is it just experience in putting the cement in there?
Sure.
Go ahead.
I'm not sure that I'm on. Could you hear me? Okay. Sure, we make sure that we're cement to surface, and so we actually, when you're pumping the cement, you actually see the cement come back to the surface, and so you know that you have cement at that point. And then also we run the cement bond log, which essentially shows us that we have a bond between both the casing and then also the formation. So that's how we test the cement, to make sure we have integrity.
Looks like I have a question for Rebecca. You mentioned that well bores are tested prior to a hydraulic fracture and again over the lifetime of the well bore. Can you explain that?
Sure. As a completion team, we make sure that that the casing is rated, right, for over the pressure that we expect to frack at. And of course, that's all early on in the design. And so as a completion team, we come in and we set a plug and we test that casing to make sure that it is going to hold to that pressure. And so then we also do that periodically during the life of the well. If we're going to do, again, the Niobrara is a wonderful reservoir, the Codell is a wonderful reservoir here, and so we're able to do refracts and trifracts, and so we actually, later on in the life of the well, we can go in and pump additional water and sand, and the reserves come up again. And so we test the casing again at that point. So again, it's setting a plug above the zone and then retesting that casing again to make sure that we have integrity.
Thank you. Are there any, I see a question in the back.
Yes, thank you. Very interesting information. Curious on the fracture from the well bore, what is the extent of the fracture network out, if you will? And then what kind of pressure, your formula is kind of exciting, but I couldn't get that figured out. So what kind of pressures do you normally run in the formations in, let's say, Weld County?
Sure. Well, first I'll tell you, what do you expect the pressure to be down in the Niobrara and the Codell? Any guess? 6,000. Okay. Anybody have another guess? It's actually about 4,500 psi is the reservoir pressure, first of all. And it's actually about 250 degrees down there. And so when we fracture, we have to get above the 4,500 psi, of course. And so, yes, around 6,000. We could be treating with friction at anywhere even 7,000 psi. Does that help? You asked another question before that. Oh, the extent of the fractures. Thank you. So again, maybe 300 to 500 feet. Sometimes we don't even get that far. We may have an effective fracture of only 100 foot around that wellbore. And again, we're just we're dividing the wellbore into maybe 200-foot sections. So if you have a 10,000-foot lateral, then you might divide that into 200-foot sections. And so you're doing each one of those independently. And so that's, it's just like the 250-foot of a vertical well that you fracture that independently. And so each 200-foot you're fracking.
We have time for just one more quick question because we're about to break.
Push anything. The question is, in the long term on your cementation of the wells, are your cement formulas always the same? And are there conditions in the vertical part of the well where the cement could deteriorate over, I'm talking about abandoned wells, so the long term, where you would then get a cross connection between formations?
I don't know of any reason that the cement would deteriorate. My hubby happens to be a civil engineer, and so we have really exciting conversations, you can imagine. But nevertheless, so this isn't concrete. This is what's around concrete, right? With concrete, you have cement and aggregate, and this is actually the cement part of it that we're pumping down there. And so it is actually designed to get harder with time, and because it actually loses water more and more over time. And so that is the really good thing about cement in our wellbores. We're, of course, building a bridge, right? That cement is getting harder with time.
Well, Lisa and Rebecca, can you stay around because it looks like that was, you probably have some more to that, no?
I was interested in the chemistry part of it.
Okay.
Cement hard.
Okay. Definitely, we're innovative. We're always changing. We're always getting something new. That is definitely something that we're always seeking as engineers. And so the chemistry has changed for certain, and getting better and better. But it's still the basic process.
Well, please thank these ladies, Rebecca and Lisa, for their excellent panel. So.